functionality built into Michelangelo. It aims to help the user determine what may be the effect of an amino acid substitution. So, let's take a mutation on the MEF2C protein from the American Journal of Genetics 2021, Wright et al., MEF2C, and we will take lysine 30 aspartate, asparagine. Okay, let's analyze. We see various toasts appearing, giving the progress. So it does it in various steps. Currently it's doing the delta G calculation, having finished the choosing of the model. We see here the features. The model chosen doesn't actually cover the entirety of the feature. In this case, we know that MEF2C is a transcription factor, and this part here is a disordered loop that disordered by itself, but wraps around the mediator complex to allow transcription magic to happen. We see over here the mutations within the MADS box domain, which forms a dimer. We can see here actually that there is definitely a dimer. And the model chosen is a Swiss model based upon the PDB file 3KOV, which is 97% identical. Let's see if this is true. Yeah, that looks pretty much the same, so that means it's very trustworthy. And a cool thing about this is that as it's a threaded model, this means that the various elements of the complex can be migrated from the template to the threaded model without it causing clashes and so forth. In this case, we can see over here that there's two chains. There are DNA chains, these two, that are taken from the template. I'll talk more later about the difference between the various models that are chosen by Venus. Okay, so now let's look at the mutation. So, our mutation is over here. We can see it structurally. If we're not sure about what the difference may be, we've got over here the difference between the two residues. So, lysine's slightly longer, and we can have a wee gander. And over here, now that while talking, the delta G calculations are finished. That is, the model of the mutant has finished being calculated, and I can see what the model looks like. So now let's look at what the overlay looks like. So now we have the wild type over here, the lysine, and over here we've got the asparagine. And as we can see, it causes the nearby phenylalanine to be pushed aside over here in yellow. But one major thing is that the lysine is actually forming a salt bridge with the phosphate backbone, and it isn't as an asparagine, which is quite bad, which would mean it wouldn't be able to bind DNA. This visual inspection over here actually allows a user to figure out what may be a valid hypothesis. And this is the main idea behind Venus, namely that the user chooses what they realize, what may be that hypothesis. Over here you can find in the documentations a brief discussion about various ideas what could be going on with your protein. But as I just said, it's 3 angstrom the salt bridge away, basically, from the ligand labeled DA, deoxyadenosine. Okay, so I talked about what the chosen model was. The residue is predicted to be buried. That is a value determined by the relative solvent accessibility, which 0 means it's completely inaccessible. 1 means it's totally solvent exposed, water in this case. Over here we see a quick delta G value. I'll mention delta G in a minute, but this is just a quick equation that taken from the recent Caldara, Blundell, and Kemp paper that simply using the relative solvent accessibility and a priori values of the mutation gives a quick delta delta G value. So this is while the user waits for the actual delta G calculations to be calculated. As I've been talking, obviously it's not too important at the minute because the delta G calculations proper have finished. Now it's part of a helix. Yes, check. It's resolved in the crystal structure. Yep. And so that's great. Now, as I said, free angstrom from the DNA. Now, over here, the delta G calculations have happened. I've mentioned this word, this mysterious word, a few times now. Delta G is the difference in Gibbs free energy. The Gibbs free energy is the potential of folding of a protein. That is, say you've got an unfolded protein. To become folded, it becomes folded spontaneously. So falls down a folding funnel, as it's called. So it tumbles down it. So it's a negative value because it's more favorable. The potential energy gets released. So in a folded state, it's got a negative value as the delta G, the Gibbs free energy. So the difference between wild type, the mutant and wild type, the delta G, this difference in Gibbs free energy, if it's negative, it means it's a more stable solution, whereas if it's positive, it means it's deleterious structurally. It's causing a destabilization. It's less likely to be folded in solution. Now, I mentioned before the Simba-I equation. That's just a simple equation. This delta G is calculated by force field methods using pi Rosetta. That is, every atom, various properties of each atom are calculated relative to each other, and this gives the energetic value. So it's predicted to be neutral. So this mutation that we saw before, where is it? Let's look at the overlay again. So going from this guy to this guy is neutral energetically. It loses one salt bridge, but and pushes another residue apart. It loses two salt bridges, sorry. But this is probably less solvent accessible. If I really cared about it too much, I could see what is the difference, what has been the gain. So it's happier in the solvent environment. That in Venus is the neighborhood of the protein. Okay, so we can see all nearby post-translational modifications. There seems to be two over here. And we can see all the nomad variants, and we can then see all the destabilizing nomad variants, for which in this case in particular there's only one. So over here we can see if there's any nearby nomad residues. And actually, the only nomad nearby is this valine to leucine, which is actually predicted to be destabilizing. As we can see, it's close to various interacting. It's close to various residues that interact with the DNA, and here we've got a phosphoserine, as mentioned before. Buried phosphoserine, and yes, so we can see that this residue is in an area completely void of nomad mutations. And if we want to know more about these various mutations, we can click on an area of interest, say the MAD domain, and we can click over here and make it do proper calculations. The neighborhood calculations, I should say, are a quick calculation. They're not as accurate as the full calculation. So say I want to do a full calculation. It's running the extra job, and now it'll give me that. If I want to see the phosphorylated model, I can click here and it will calculate the phosphorylated model. Now, I mentioned before that Venus chooses the model for us. So, one can control what model is selected. I mentioned before that that the AlphaFold model, even though AlphaFold is generally considered to be more accurate, in some cases it's a bad idea, and actually in this case it is a bad idea. Because we're dealing with a dimer. AlphaFold does not do dimers or complexes. So say I disable all of these, and so it only will show me a AlphaFold model. So now it's doing its thing again, and it's chosen this. Let's see what AlphaFold has given us. Ooh, aye. So let's look at the confidence over here. So red is good confidence, yellow is no confidence. As we can see over here, this is the MADS domain. Let's go back over here and click on the box. Yeah, as said, this is the domain. So this is actually a dimer, but we're only seeing it as a monomer, so half of it's missing, so that's not quite good. Obviously, this is not great, and that is why the Swiss model the threaded model, so Swiss model, albeit less accurate and less complete in terms of lengths, as we saw, it didn't have all this extra spaghetti that binds to the mediator complex in the DNA. It's more reliable. Yes. The other settings I should say in here are to tweak what gets chosen and how accurate, how lengthy the calculations are. However, tweaking the number of cycles to the max and how large the neighborhood is, or changing the score function to a Cartesian score function, generally doesn't improve the delta-delta G calculations too much. The thing that will change it is the model chosen, but generally between different models the accuracy isn't too much. But as I said, if you're trying to look at a mutant such as this one and you're lacking the DNA, it's quite important, that feature. So, and lastly, say we're quite happy with our results, and we can go and inspect the various sources it came from, say Phosphosite Plus for the phosphorylation, ELM in case we broke a signaling molecule, a signaling sequence. We can share a link to recompute these values, or we can tweak what we see over here and making it ready for export into Michelangelo proper. That is, if I say I want to show the overlay on wild type, let's go here, or I can do, so I could do export, which is up here. Create a shareable Michelangelo page. I want these two because I'm showing a overlay, and now the text has come up and everything's loaded. I realized that just now I did export the version which was with the AlphaFold model, which wasn't the better model, but hey. But now, say I had used the correct model, I can say that I can write my comments as normal. This is residue, and add my prolinks as normal, as you can do normally within Michelangelo, because this is now a proper Michelangelo page. Lovely. and I can save the changes, or if I'm really not pleased with the page, I can delete it. So now this link, when shared, will result in, can be shared, and the user will, and the reader will always see this page that's just been generated.